Okay, so today we're going to build a class for doing fractions because I want to. So I have a fraction class. I have to initialize this class with something. So initializer. And what do we need for a fraction? Good start. Okay, so I need to take in a numerator, and let's say that's an integer, and the denominator, which is an integer. And I need for this fraction to know that it has a numerator and to know that it has a denominator. What else do we have to do with these? Okay, so we can define a representation for both the string and the representation itself. And I can say, let's return something over something. Self.numerator, self.denominator. Okay, and let's read this in, see what we got so far. I can have p, and this can be a fraction, a half. Great, so we can print out something that looks like a half. What about q equals a fraction, 2 quarters? Do you think we should allow stuff like this? Well, it depends on our design philosophy, right? So I would say it's better to reduce the fractions, right? Because then otherwise every time we do a multiplication or an addition, things are going to grow really, really, really quickly. So what I'm going to do is just import the GCD command for math. And I can say we have the GCD is equal to the math.gcd. Do you guys know what the GCD is? What's the GCD of 3 and 9? All right, I believe you. Numerator, denominator. So this needs to be integer cleared by the GCD, and this needs to be integer cleared by the GCD. So we can have q, and now that's a half. Okay, so what's the arithmetic now that we want on fractions? Right? Addition, multiplication, subtraction, division. And then we have to talk about other things like how we order these fractions. But let's just focus on... yeah, probably. We should also care if one of them's 0. But at the moment, let's just pretend these edge cases don't exist. But did everyone hear what was said? Yeah. We should worry about what happens when we have a negative over a negative. We should worry about what happens when we have 0 over something, or 1 over 0. But yeah, anyways, let's get some core functionality before we worry about the edge cases. So we have our representation in a string, which is good, because now we can look at the things that we're building. What's the easiest? Let's do, what is the easiest of the operations to do? Exactly. So we have to take a self and we have to take another, right? 2 objects. How do we multiply 2 things together? So we have to multiply the numerator, self.numerator, times other.numerator, over self.denominator times other.numer. Now what? Well, I'm missing one thing. What do I have to return here? I heard it. What object? Fraction object. Okay? And notice that because I'm returning a fraction, when I instantiate the object, it's going to clear the GCD for me. So the GCD being removed is going to happen in one place over and over and over again, right? Which is cool. So I don't have to continuously clear GCD, so no matter where I'm working. So I'm just going to bump that up a bit. Go back into here. Reload it. So let's see. Let's get p, which is a fraction, a third. Q, which is a fraction, 3/7. What? Oh, fraction. Okay, so I have p, I have q, and now I can do p times q and get the wrong answer. All right, debugging. self.numerator, other.numerator, self.denominator, other.numerator. So what happened here? What? All right, denom. Thank you. So p is equal to a fraction a third. Q is equal to a fraction 3/7. And p times q. Still not working. Oh no, working. The 3's cancel. Yeah? Maybe I picked bad examples. 3 ninths, tenths, 11ths. P times q. Oh, geez, the 3 cancels again. Well, whatever. One more try. 7/11. P times q. 7/33. Great. I just want to take a minute and appreciate this. A third. Python doesn't have this number, right? Like, even though this times this is 3, okay? Right? Like, it's weird. Right? Like, floats are weird, right? Why isn't that giving me 0.99999 back, right? So, I've actually shown you the fundamental building block of exact computation now. Symbolic computation. Rationals are the first thing that you would need to start working exactly, right? So we shouldn't overlook the relevancy. Is that a word? Relevancy? Yeah, I think so. Shouldn't overstate the relevancy of introducing the number 1/3 into the system, right? A number that previously we did not have access to, right? So this is not a, well, it seems easy, but it's not. We haven't introduced trivial behavior to the system. This is a very robust behavior. In any case, what else do we need? We need an add one, right? So how do we add two things together? Yeah, we just sort of cross multiply. We don't need a common denominator. We're just going to over multiply. I have to erase all my nice pictures. Chalk. So what was I talking about? Addition, right? Okay, so A over B plus C over D is equal to AD minus BC over BD. Okay? This may not be simplified, but our constructor, our initializer is going to handle the simplification, right? So I need to do, what do I need to do? Okay, let's just be easy on ourselves. Self dot numer, self dot denominator, self dot numer, self, yes, it should be other. I hate self so much, so much. Denominator. Okay, so we should return a fraction. That fraction is A times D minus B times C over B times D. Okay. Wait, what? I'm only off by a sign. I'm off by more? Thank you. Okay, so what do we got now? We got P, that can be a fraction, like a third. Q, which can be a fraction, like 6/33. Oh, no, that's a bad fraction, because we need to be able to confirm it. 2/5. So we have P, we have Q. I want to do P plus Q. So before we look at the output, we need to predict it, right? Like good programmers. So what is a third plus a fifth? 15th, that's 5, 6, 11 15ths is what I get. This is cool, right? We've overloaded the plus symbol at the interpreter level. Not many languages give you access like this, right? To just let you go crazy with real binary operations at the top level. Okay, so what else do we need now? Not a trick question, right? We just need the other operations. So which, Division and, okay, but I don't want to define division and subtraction. Because really, we have to think like mathematicians and lazy programmers. Remember? We don't want to define subtraction. We want to define negation. And then just add the negation of a number. Right? 2 for 1. Same thing with division. We don't want to define division. We just want to define inversion. And then multiply by the inverse. Right? Okay, and you'll see how nicely this will work out. So we want to do something like define negation. Good, it's blue. That means it's the thing I want. So what should the negation of a fraction look like? Yeah, pick one. It's either the numerator or denominator has to become a minus. So I'll just do it in the numerator. Exactly. Self-denominator. What about an inversion of a fraction? Geez, what is inverse? Forget. Invert. So how do I invert a fraction? Swap. Okay, so now I want subtraction. Okay, well, let's go into the, shouldn't go too far. Let's see if what we got is working. P fraction, 2/3, negative P, inverse P. Great, works. Okay. Bless you, bless you. Definition of subtraction. Self and another object, right? How do I subtract? Well, return self minus other. Sorry. Plus minus other. Right? I'm adding the negation. Right? That will work for those people looking skeptical. Because minus is both a binary and unary operation. Right? So it checks that it's, first it will check the unary operator, then it will ask if it's a binary one. Okay, so that is subtraction. And here is division. Any guesses? How do we do division? P minus Q, P divided by Q. Damn it! Did I spell something wrong? Sorry. Div defines integer division. True division defines true division. So I could have done this, actually. Maybe not. Something is wrong. Okay, let's try again. P divided by Q. Come on. Yeah. Is that correct? Yes. Right, because this should be P times inverse Q, which is going to give you 5/6. But look how nice this is. Right, this is defined all arithmetic over integers, over fractions. Very compact. And now I only have to maintain like a couple things, right? As long as negation, inversion, provided negation and addition are working, then subtraction is working. Provided multiplication and inversion are working, division is working. Right? So this is even easier to maintain, right? Because the correctness of some of your methods are a consequence of some of your other methods being correct. And I know that seems kind of shitty because a error at the top of the chain is going to screw everything up. But it's better to be able to isolate your bugs downward. Like you can always say, well, the problem can't be, like, I can look at, if there's a problem in true division here, I can look at it and I say, it's impossible that there is a bug in here, right? The bug has to be somewhere else further down into the code. And this is just too simple of a statement to screw up anything. Okay. Just so pretty. Track one. Okay, what are we missing now from the fraction class? Oh, besides the edge cases, which we're not going to implement. Okay. Well, what else do we want to be able to do with objects? Maybe I'd like to do something like this. Or like this. Okay. Or even this. Okay, I want to see how lazy you guys are able to be. So here are the rest of the binary operations that we have to introduce. How many of them do I need to explicitly define? Which ones? Let's pick the less than. This one? And this one? That's it? Who agrees with him? I agree with him. Who agrees with him now? Everyone. Yeah, we only need these two. And everything else is a consequence of these two, right? Let's understand why. Okay. So I'm kind of cheating because remember, these are all Boolean operations. So we still have our friends and or not. Right? Specifically, we're going to need the not operator. Okay? So what does it mean for it not to be the case that x is less than y? Strictly less than y. Okay, so we got that one. What does it mean for, well, x is less than or equal to y is logically equivalent to x is less than y or x equals y. Maybe you guys don't like this. Okay, so now I have greater than or equal to, less than or equal to. What is this? Strictly greater than y. Do we have all of them now? Strictly greater than y, strictly greater than or equal to, less than or equal to, less than, and equal. Yeah. So you get all the comparison operators by defining one of the strict ones. We typically pick less than because you usually sort lists in ascending order. And then we need equal, which we haven't also discussed. So what should it mean for two fractions to be equal? Remembering that we were the ones who invented and set up the fraction class, right? Because it's relevant. Another student in my last class pointed this out to me, and she was right. How do we, okay, so like, first of all, should we let these two things be equal? Oh, sorry. Okay, justify. Okay, so I'm going to play devil's advocate. Why would we make these things the same? They're at different memory locations. They have different pointers. I shouldn't expect, these two objects aren't the same. Yeah, that's a very good justification, right? Our design philosophy was to introduce fractions. In our design philosophy, fractions have a numerical equivalency that should be more important than the fact that they're existing at different memory locations. Right? So there's never like a true answer to any of these questions. But if you make a design decision, you should be able to have a justification for why you made that design decision. It shouldn't be arbitrary. So in fact, I would agree with you that this should return true because our philosophy is that we want to introduce a different number system into the system. We can always overload this. Right? You have equal and you have is. Right? Is should be the thing that asks, are these really the same object, right, at the same location? Okay, so what about situations like this? Oh, up. Oh, I didn't actually execute that. Fraction a half equals fraction 2/4. We haven't told how to do the equivalence in the first place. So I know it's going to reduce. So I think the answer to this should also be yes. Okay, so let's go into our code. And let's define what it means for two objects, fraction objects, to be equal. What should it be? What should I return? since we've agreed that all fractions are going to be simplified, two fractions are equal if their numerators and denominators are outright equal, using the integer comparison, right? Because it's important to note that we're using the equality of integers to define the equality of fractions. Like we're borrowing from a number system that's somehow below us. Okay, so let's try seeing what happens if we do this. So now it should be the case that this fraction is equal to this fraction, which is further equal to this fraction, 8/16. Great. But it's not equal, whoops, let's try 2/5. False. Great. Okay, so now we need the rest of the comparison operations. We need define less than. What does it mean for one fraction to be less than another fraction? I'll write it on the board what you think, but don't hurt yourself. What does it mean for A over B to be less than C over D? Come on, smart class. Yeah, exactly. That's okay. You gave the best. Yeah, you guys are the smart class. Okay, the other class said convert these to floats and compare. Why is that the wrong answer? Because the whole point of this is to not use floats, right? To not introduce error into the system. They're like, let's introduce the error to do this. I'm like, oh god, no wonder the other class is a smart class. AD has to be less than BC. Although, where is he? Ivan, you made an assumption here. Yeah, I'm positive you made an assumption. No? Ivan, what happens if I choose negative numbers?
Oh.
Yeah. Okay, so we've made an assumption here, yeah? That we've assumed that these are all positive integers. Okay? So the rest of the stuff that I'm going to do today, we're going to assume that these are positive integers. But it's very easy to modify the proof so that you just basically go through the proof and say, let's do them that they're all positive. Now let's do another proof where this one is negative. Right? Because you don't make them both negative because it becomes positive. And then you do another proof where these are both negative. So you have to do three proofs that all look exactly the same, except like sometimes you have to flip the sign and other times that you don't. There's a cheat word in mathematics that you guys don't get to use until like you're real mathematicians. It's called this. Without loss of generality. I'm going to do the proof once and you guys do the other two. Wow. Yeah, you can't say that because you guys will write that down and not know what it means. Without loss of generality, you write the answer. Yeah, but you see that's what that word means, right? It means that we have to do one proof several times, but the cases are so similar that we're not going to bother writing it. Right? Something like that. Okay, so so you see what we did here? Like this is really a less than operation over the rationals, right? Which is the technical term for fractions, being defined using the order over the integers. Right? So we're taking a number system and we're lifting it into another system and making it more robust. But we're borrowing, right? And the integers, in fact, borrows the ordering from the natural numbers. And the natural numbers, well, are defined with an ordering. I could go on forever. Less than. Okay, so return, what did I say? Just let me go up here and grab this. This seemed to be useful. A times D has to be less than B times C. Yeah? Okay. Let's do the rest of them. Let's make sure this works. So is fraction a half less than fraction a third? Who has the bigger piece of pie? The guy with a half a pie, or the guy with a third of a pie? Half a pie. Nope, I lied. Third of a pie. I'm joking, right? What did we do wrong here? What did I do wrong? That's correct? Oh. I'm with you guys. Sorry, I just got really distracted by pi. I really should eat breakfast before I see you guys. Okay, let's define the rest of them. Okay, so define less than equal, right? And remember, we want to be lazy, right? So less than equal is easy. Return self is less than other or self is equal to other, right? Define greater than. That should be return not self strictly less than other. Is that it? I think that's it. Define greater than or equal. That should be return not, no. That should be this one. And this should be this. Confirm? Someone? All right, well, we can just test it. So this should be false, which means the other thing should be true. Which means this should be true, which means this should be false. Okay, so let's check some of our edge cases. Nope. Yep. 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 Okay, so let me do this. I'm going to define from random import random integer. Let's define a list of random fractions. Did I call it fraction or fractions? I think fraction. Random integer from -5 to 5, and a random integer from 1 to 10, right? Because I don't want to divide by 0 for anonymous in range 10, right? Just to use what we learned the other day. So there is a list of random fractions, and since now we've defined a less than operator, we get this. Okay, so this is the launch point for like this talk I gave to the other class, and maybe I can give it to you guys in 15 minutes. Like none of it is testable, so I can go through it kind of quick. Because I want to, okay, so I sorted this list, but we took it for granted that I defined a comparison operation which is going to give us sorted unique lists. Okay, the question now is, suppose we define a less than operator on some unknown object. What precise properties does that less than operation need in order for us to be able to sort a list of those objects? Right? It's not clear. You guys are so used to working with numbers. Numbers are trivially organized. Right? Numbers are designed so that one is bigger than another one. But what happens if I have like a class of cars? Right? Is Toyota greater than Honda? I don't know. Right? I have a Volkswagen, so. Right? So tell me what properties does our less than operation need for us to define sorting? I want to prove to you that as soon as you start looking at a problem closely, it becomes math. Like almost without exception, right? Don't try too hard. I don't even think you have the words to be able to express the answer. So I've literally bracketed the slides which you don't have to study with a not testable slide. Right? And people still asked me what was testable after the lecture, so I just give up. So this relation operator, this squiggly one, is meant to denote like arbitrary relationship operators. It's a symbol that you read precedes. Right? So if we talk about ordering, we can talk about two elements we can talk about one element preceding another element, or one element succeeding another element. Right? So this, when I say something like this is to say that the element A precedes the element B in a list where you would order it. Now, to be a partial order, you need to be at least reflexive, antisymmetric, and transitive. Reflexive means that for every element in your set, you compare to yourself equals true. So I'm going to borrow the ordering on the integers, right? Because we don't have really any other things that I can use. So the integers is a partial order. and it's a total order. But you have to be a partial order before you can be a total order. So the integers. It is true for the integers that for any integer x, x is less than or equal to x. Right? Thereby the integers have the reflexive property on its less than operator. Is the integer comparison operation anti-symmetric? That is to say, if a is less than or equal to b and b is less than or equal to a, then a is equal to b. Yeah? The other class asked why we want anti-symmetry and not symmetry. Symmetry is the opposite of this. Symmetry means if a compares to b, then b compares to a, which would be a disaster if we needed that. The only that basically means you have equivalence, right? If it has to be, if we're allowed to say a is less than b if and only if b is less than a, right? That will never happen. So you can't have a symmetric property on an ordering relationship. We need an anti-symmetric property. The transitive property is easier to understand. If a is less than b and b is less than c, then a has to be less than c. It's also called the triangle inequality in some other cases, but it's properly transitivity. Okay, so this gives us a partial order. So smart class, there is one condition missing that we need. What is it? No, we don't need equivalence. Yeah. Well, suppose you give me a set of integers, and I tell you how to order the even ones, right? Is that an ordering on the integers? I tell you that 2 is less than 4. I've told you that 2 is less than 6. You're like, is 2 less than 5? And I'm like, I don't know. Right? Is that a reasonable ordering on the integers? You want to be able to compare any two elements from the set that you're working in. Yeah, exactly. You need to say, look, whatever relationship you define, you have to give me the relation on every pairing in my group. Not a subcollection of the pairings, all of them. Right? That's the difference between a partial ordering, an ordering of the even numbers, say, and a total ordering, or an ordering of everything. Right? So that's, yeah, the other class wasn't able to converge on that. They actually argued with me for about like 10 minutes that that's not like an implicit assumption. I don't know. They're the dumb class. For a reason. Sorry, YouTube. I mean, you're not the dumb class. You're just less smart than this class. Right. So in the last 10 minutes, I'm just going to show you a little bit of math, which you don't have to remember or understand or reproduce. Right? So this is not testable. Not testable, not testable, not testable. Okay? So what we have is, we have a rule here, in fact. Right? We've defined a ordering on the irrational numbers. My question is this: have we defined a total ordering? Okay, so let's go through all of the conditions, right? Reflexivity, anti-symmetry, transitivity, and totality. Is this symmetrical, right? So that is any element, any fraction. It is the case that for any fraction a over b, it is the case that a over b is less than or equal to a over b. Maybe we should write that on the board. Okay, so we want, what did I say? Reflexivity. Right, so that if you take any element from your group, this means that A relates to A. Right, so we're going to specifically use this. So we take A over B, which is a fraction, and is it the case that this is less than or equal to A over B? Right? So I have to prove this somehow. So proof, right? I love proofs, guys. Proofs are my jam. It's okay, proof. Okay, so what do I need to prove? I need to prove this. So we have from We know that this is a total ordering, right? Which means it has the reflexivity property, which means I know that AB is less than or equal to in the integers to AB. Yeah? Which means by definition, we have that A over B is less than or equal to A over B. Okay? Which implies reflexivity. See, that wasn't too painful, guys. You don't have to be afraid of proofs. They're your friend. What do you think you're doing when you're writing computer programs? You're writing proofs, right? You can prove your computer programs, right? So it's impossible that you guys aren't also good at proofs if you're good at computer science.
Help us prepare for the quiz tomorrow.
I can write it for you. $100. Okay, I'll help you. Okay, I will help you. Okay, let's do transitivity now. That one was not overly easy. And then I'll let you guys go. Because I'm just like giggling that I'm teaching you algebra in a computer science class. Like, this is important, right? Like, you can't just, I'm trying to give you the impression that you can't just, like, willy-nilly define a less than operator on an object and then expect to start sorting things, right? You need several properties of your less than operator before sorting becomes possible. And those properties, again, reflexivity, antisymmetry, transitivity, totality. And you'll learn more about this in algebra. And you'll definitely learn more about this in Foundations of Computer Science, which I think you guys are going to take in the third year. Foundations of Computer Science. You guys know you're computer scientists and not computer engineers, right? Can any of you answer this question? What's a computer? Ah, yeah. Old joke. I get it, yeah.
Something that can process data.
No, not good enough, right? This is I applied to teach the Foundations of Computer Science class next year, right? It's my #1 request. And I always open the class with that question. Can any of you computer scientists who are here in your third year tell me what a computer is? Blank stares. No one has ever thought of this question, right? And of course the answer is 4 months of development of mathematical properties, right? It's very interesting. Are there problems that computers can't solve? Yes. Prove it. 4 months later. How much time do I got? We can do transitivity. I just can't write it very nicely. A over B is less than C over D, right, in the rationals. And, A over B, C over D is less than or equal in the rationals to E over F. And we should be able to imply from this, eventually, that A over B is less than or equal to E over F. Okay, so what do I got? I got by definition. Okay, so this is kind of separate. Okay, so by definition, this is if and only if AD minus BC, if AD is less than or equal to BC in the integers, and CF is less than or equal to DE on the integers. Well, this means that I can multiply this by F on both sides, and provided, remember, I assumed everything was positive. Right, so I get ADF is less than or equal to BCF, and CF is less than or equal to DE. What do you see here?
Multiply B on the right.
No more multiplication is required. I know that CF is less than DE, right? So I can replace this CF with a BDE. I just made it bigger, right? CF is less than DE. So if I replace CF with something bigger than CF, this equality will still hold. I just made it bigger. It's more big than the thing now. What do you see now?
We can cancel out the D.
Cancel out the D. What are we left with? AF is less than or equal to DE, which by definition means A over D, B. You guys. A over B is less than or equal to E over F. Proof. Oh, come on, simple proofs, simple proofs. Math is fun, guys. I can show you that math is fun. I love this kind of stuff. Oh, I won't do anti-symmetry. I only have 1 minute left, so you guys go do it. They're in the slides if you really want to go look at them. Yeah.
We're learning this right now.
Oh, cool. You need to know it. So hopefully they now ask you to do transitivity or something on your exam. Right? Okay, remember, guys, I have office hours today. If any of you are going to visit me,